Okay, so welcome everyone to the first of the 6 sessions that comprise your final week of HSMA training. So it's quite intense this week if you're planning on going to them all, but there's lots of good stuff that we've got planned for you this week, including lots of stuff around natural language processing, some more stuff around reinforcement learning that Mike will take you through, some of the advanced forecasting stuff that Tom will take you through. Sean's doing a network analysis session, and of course this morning as well. So this session is really a direct continuation of the last session we did on agent-based simulation, particularly using Mesa, the Python package that's really good for this kind of stuff. And you'll recall last time that we started building an agent-based simulation of the spread of a disease. And we looked to see how movement and transmissibility would affect the spread of that disease using an agent-based simulation framework. So what we're going to do is we're going to build on that model today. Specifically, we're going to build in some concept of people becoming immunized, perhaps from a vaccination program. So nice and timely. And see how we can use the model to try and predict what the impact of something like that might be. What I'm going to do first, though, is to go through and recap the model that we built last time, because it's been a while since we looked at that. So this is a chance just to go back over this model. Remember how we built it up, because I'm going to hand over to you quite quickly this morning to get you to work in your groups to actually build in this immunization aspect. So you'll need to build into the previous version of the model. I'd recommend that you use the version that I'm using, i.e. the version that I posted on the Slack channel, just to make sure that you're working with working code, in case you didn't manage to finish off the exercise from last time. So just to make sure we're all at the same point. So let's recap the model that we built the last time. So let's bring this up. So you'll recall that I said that in Mesa, you effectively have 3 .py files. One of them represents your model, and it's where all the magic happens, and you define how the model works. And that's primarily made up of various agent classes, which represent the different types of agent that you've got in your model. Maybe you only have one, but it might be you have more than one. We have a model class that effectively runs the model, defines what happens at each time unit in the model, and also controls the agent's operation. And we have optionally a number of data collectors, which are ways in which we will collect important data that we want to look at coming out the other side of our model. So various functions that we can call. And that's basically our model .py file. And then we have a run.py file, which basically just tells that's the one we run to kick everything off. And there's 2 ways we can do that. The first way is to essentially run it by launching a server, which will then visualize the model on a server. And you saw an example of that last time, and we're going to run that again in that way today. But the other way, which I'll show you later, is that we can get the model to not display all those nice visualizations, but instead to run the model lots and lots of times with different combinations of parameter values to test what's happening. And if you're using an agent-based model in real life, that's probably what you would do. So you would typically use the kind of visual aspect to show people how the model's running and generate some discussion about what's happening. But then to actually generate the results that you'll use, you would then sort of run it in batch. And then the third .py file you only need if you're running this live visualization, which is the server.py file, and that basically defines what your visualization will look like. So it's going to open it as a server, which will launch a browser, and that browser window will have various visualizations on it, and this is where you define it. But you don't need that if you're not running the servers. You only need 2 of these for any model, and then optionally the third one. So let's go back through the main model.py file to start with, because that's where all the magic's happening. So we had a number of imports that we made at the start. Critically, from Mesa, we import the concept of an agent and the concept of a model. These are key to our agent-based simulation. So we're importing both the agent class and the model class, and we'll need both of those for pretty much any agent-based simulation that you care to design and build. We also imported some other stuff that was useful for our particular model. So from the Mesa.time library, we imported a module named random activation, and that's just basically a way in which we can define the order in which agents act, which, if you recall from last time, we said is actually quite important in this model, because of course if somebody moves who isn't infected before somebody who is infected moves into the same location, that's going to be very different to if the opposite happened, because in one scenario they will escape any chance of being infected, whereas in the second scenario there's a chance they may be infected. It won't always matter the order, and if the order does matter, as it does here, then you probably don't want to use a random activation unless you have no other data, but that's what we're doing here, just to show you how this works. We also imported the grid type that we want to use, what the environment essentially they will move, our agents will move around in, and we imported something called a multi-grid, which basically means that we can have more than one agent per cell, and that's obviously very important in a model like this where we're doing disease spread, because we need people to be in the same location, because that's where infection happens. And then we imported this idea of a data collector, which we'll come back to in a second. And we also imported the random library because we're going to sample from distributions. So then we defined our person agent class. So we've only got one type of agent in our model. It represents a person, so we've just got it person agent. And if you recall, we said this is an example of inheritance, because what we can do is we can inherit the agent class from Mesa. That's the parent class, because Mesa has already defined what an agent is and done all the key stuff to define to Python what an agent is in an agent-based simulation. So we can inherit all of that stuff and then just add the bits that are important for our particular model. So remember, to inherit something, we simply pass into our class definition into the brackets after the class name. We pass the name of the parent class, and that basically means this is a child of that parent. So inherit all of its properties, and then I'll tell you all the bits that I want extra, or bits that I want to change or remove. And in our constructor, we can call the super keyword here, which basically tells it to, super basically refers to the parent. So this basically means from the parent, run the parent's constructor with the passed in unique ID for this agent and the model that this agent lives in. And so that means that we don't have to do all the sort of general setup of what an agent is. We can then just worry about all the bits that are unique to our particular model. So we can define some attributes here that are important. So we've set a transmissibility, which remember is the basically the probability that an infected agent infects a non-infected agent if they're in the same location on any given time step. We had a level of movement, which is basically the probability that an agent moves on any given time step. We've got an average length of the disease, from which we will sample from an exponential distribution, but that gives us the average length of the disease should this agent become infected. And then we work out whether they're infected at the start of the model or not. And we do this by passing in a threshold value called an infection value. And as you've seen lots of times now, we can use the uniform distribution between 0 and 1 to randomly sample a number. And if it's less than that threshold, then we'll say that this agent is infected at the start. So we can update, we have a little Boolean attribute that says they're now infected. So we set that to true. And then we calculate their disease duration by sampling from an exponential distribution, passing in the mean length of disease that we've got stored now against that agent. If they're not infected, then we just set that infected attribute to false. So essentially, we set up our agent. They've got a probability that they will infect other people. They've got a probability they'll move on any time step. They've got an average length of disease, and then we work out whether they're infected or not at the start. And that's our constructor. Then we set up the various functions within the various methods within the agent. And typically, within an agent-based simulation, an agent will have multiple methods. Typically, they'll have some way to move around an environment. They'll have a number of methods that will define the actions they take other than movement. And they will need a step method, if you're building this in Mesa, to define what happens at each time step in terms of the order in which all this stuff happens and which functions are called and which aren't, etc. So first, with our movement function, which was called move, we just do three very simple things here. We, if this move method is called, it means the agent is going to move on this time step. So we grab the possible locations that it could move to by using this handy get neighborhood method of the model.grid from Mesa, and we just pass in my own position of this agent, self.pos. We specify that it's a more neighborhood, which just means you can include the diagonals. If that was false, it would only include the cardinal directions of north, south, east, and west. And we don't want it to include the center because that's where I am. And if I've been told that I'm going to move, then I can't choose as one of my locations where I am now, because then I wouldn't move. Then from those possible locations, I select a new position at random. In this particular model, again, if you were doing this for real, you may have some logic that defines where people move, but we're just going to assume people will move randomly. So they just simply randomly select one of these possible locations from this list, and then we move the agent just by calling the .moveAgent method. And all we provide to that is the itself and the new position that we've selected at random here. So that's all move does. See where I can go, what are the grid cells I can move to, select one of them at random and move there. That's all it does. Then we've got the infection function, which is just called infect. In this one, first thing we do is have a look to see who else is in this cell. Because obviously we can only infect other people if other people are there. So we can grab a list of cellmates. This will list all of the agents, including the agent itself, this agent, who currently occupy the current cell. So we can use the get cell list contents method, and we pass in our current position here to say this is the cell I'm talking about. It's my current position. Then we need to check if there are other agents here. In other words, is there more than one agent in this cell? Because if there's just one, then it's just me, and there's no point doing anything else. I can't infect anyone. But if there's more than one, then for each inhabitant in that cell, for each of those agents, then check whether they're infected or not. Because if they're already infected, we can't infect them again. But if they're not infected, then we'll randomly throw the dice. And again, we'll use this uniform distribution, check it against the level of transmissibility. So if the transmissibility is 20%, then if it falls between 0 and 0.2, then we're going to infect someone. And if that happens, then that inhabitant becomes infected. We set their Boolean flag to true. And then, as we did at the start, if they're infected, we calculate their disease duration by randomly sampling from an exponential distribution using whatever mean length of disease we've passed in. Now, this protects, because obviously one of the inhabitants in the loop will be this agent, the agent that is being run at the moment. And obviously we can't infect ourselves, but by putting in this logic where we only infect them if they're false, that doesn't matter because we've only got this far if we are infectious. We can't infect other people if we're not infectious. And therefore we'll never get down to this bit. So we would check ourselves and then note that we are infected. So none of this will happen. So that's the infection. see who else is here. If there's anybody else here, randomly, and check whether they're infected or not. If they're not infected, then throw the dice and see if we're going to infect them. And then the final method in the agent class is the step method, which basically just says all of these things you're going to have to do in this order on each time step of the model. So the first thing we want our agents to do here is to move with a given probability. And remember, we've got a level of movement set up which defines the probability that an agent will move on any given time step. So again, we randomly draw from a uniform distribution. If it's less than that, whatever that level is, then we'll call the move method, which we've defined above. So if you're going to move on this turn, then call the move method, and that will define exactly what you need to do. And then, regardless of whether or not they've moved, the other thing they need to do is begin infecting people if the agent is infected. So if they're not infected, none of this will happen. But if they are infected, then we'll call the infect method, which we've just defined up here, where it'll check to see if anybody else is there, and if they are, it'll work out if they're infected or not, and if they're not infected, then it may infect them. If they are infected, though, there's something else we need to do. We also need to decrement their current disease duration by 1 time unit. So if our time units are representing days, for example, and they're infected, then on each time unit we want to decrease their remaining disease duration by a day, because another day has passed. So we decrement that here and store that against the agent. And then we ought to check to see if the disease has now run its course. So if we've got less than or equal to 0 left on the disease duration, then the disease has run its course and they're no longer infected. So we can update the infected attribute to false. So they will now no longer be infected. So all we're doing at each time step is working out if we're going to move, and then if we are, calling the move function. And then if we're infected, calling the infect method, and then decrementing our disease duration. And then if that's now, if the disease has run its course, then update to the fact we're no longer infected and therefore infectious. So that's the agent class. And that's all we need to do for the agent class. We then define the disease model class, which again we set up using our constructor here, and we set up a number of attributes. This first one, you'll see why we have to have this thing called running and set it to true a bit later. But just know you have to put that in if you're going to use batch runners, which you typically will. We also have a number of agents, how many agents we've got in the model, which we will pass in with this value n, and we'll store that against the model. We're going to set up a grid, which is the multi-grid that we imported, which will have a certain width and height, which we'll pass in when we set up the model. And remember, the multi-grid just means you can have more than 1 agent per cell. And we set this third attribute to be true, which just says make it toroidal, which basically means if they're on the edge of the grid, so if they're on the far right, and then they move right, then they'll appear on the far left. And that's all a toroidal grid is. And then we set up a schedule, which is just determining the order in which agents will move. And remember, we imported a random activation type schedule, so we're going to specify that we want them to move in random orders, our agents. Then what we need to do is create our agents. So if we've got 100 agents that we've passed in as being the number of agents we want, then we'll have a for loop that runs 100 times. And because this is object-oriented, we create a new instance of the agent class. We pass in all the information that we need. So the infection, the probability that they're infected at the start, the transmissibility, the level of movement, the mean length of disease. And then we just add that agent object to the schedule that's being stored. This is the random activation schedule that we defined here. We add that to the model schedule. So then the model now knows I've got this agent I need to deal with. And then we need to place them on the grid somehow. And here I've just got a simple logic that basically says, ideally I want my agents kind of in their own cells if possible, to spread them out so we haven't got people in the same location at the start. So it'll try and find an empty cell. And if it can find one, then it'll place the agent there. But if that fails, I can use my try and accept logic here to say, try doing this. But if you can't find an empty cell, then this will fail back with an error. So then that will be captured here. and then the except statement will run, which basically says, okay, well, if you couldn't find an empty cell, then basically pick a cell at random, pick a random X coordinate, a random Y coordinate within the range of the width and height, and then place the agent at those coordinates. So it'll always try and fill up the grid first, and then it'll just randomly pick where to put them if it's full. The other thing we need to do is create a data collector, and we came onto this towards the end of the session last time. Remember, the data collector is the thing that we can use in Mesa to basically monitor the results that we want to look at over time. And so we've just got one at this stage, which is basically monitoring the total number of people who are infected. And we specify that as a model reporter. You can have agent reporters too, but don't worry about that at the moment. And we call that total infected, and we specify here the name of the function that's going to calculate the total number of infected, which we define down here. So we'll have a look at that in a second. But that basically says to get that number, then this is the function you need to call. That's the function that will calculate it for us. And Mesa, with its data collector class, will do all the magic for you. It'll do all that collecting over time for you. And the last thing we need in the model class is, again, a step function, just like we had for the agent. And here, we basically just tell it to increment the step of the schedule. So the schedule is the thing that's running the model by organizing the agents and how they act. So we just tell it to step, call the step function of the schedule, to say move on a time step, do all the things that a time step needs, which will include calling the step function of the agent, which is all this stuff up here, for each agent in the order that we specified, which remember is random. And the only extra thing we're going to put in is after all the agents have acted, then tell the data collector to collect the results from that time step. So we can call the collect method the data collector, and because Mesa's got all this predefined, it'll basically say, okay, I will now collect that data. And what it does is it calls the method that we set up below to calculate the number infected, and it stores that and reports that for us. And so here's the function that we write outside of both of the classes, which will calculate the total number infected over time. We pass in just one thing, which is the model. That's the model object in which they live. And all this does, it says, start a counter at 0, total infected, then grab me, using a list comprehension, a list of trues and falses, which basically indicate whether they're infected or not. So for grab from each agent, their infected attribute, which remember is a true or false Boolean, in the schedule .agents, which is basically where all the agents are listed. So we can grab the infected status. That'll just give us lots of trues and falses, indicating whether or not they're infected. And then we can just loop through that list. And if every time we get to one that says true, we can increment our counter, and then we can just return that number. So if there are 3 trues, we count 3 trues, and we now know there are 3 infected at this time step of the model. So that's the model. In essence, you've got some imports at the start that we need from Mesa. Then we've got our agent class, which is comprised of the constructor, a movement method, an infection method, and a step method. And then our model class, which is comprised of the constructor, along with a step method. And then outside of that, we've got our data collection functions, of which we've only got one at this point. So that's the model.py file. And then in the disease run.py file, remember, if we're just setting this up so that it runs on a server so we can view the visualization, then we can literally just have these 3 lines of code exactly as they appear on the screen like that. And that is all we need to put in our run file. So then if we are running a server, the last thing we need to do is set up the server file. And this basically just tells it how to visualize stuff. So we import everything from our disease model. So we've called our file disease model. From that, import the disease model class, so the model class that we wrote. That's the bit we need. And then import some various visualization stuff, including a canvas grid, which is how we'll view our agents on the grid, a modular server, some user settable parameters, and a chart module, which will allow us to plot things over time. So we've got the total number of infected that we want to plot over time. And then we just have a portrayal function, which basically defines how we draw agents to the screen. And we set that up as a dictionary in here. So we set up a portrayal dictionary, which defines various things such as the shape of agents. So here we want them to be circles, we want them to be filled circles, and we want the radius to be 0.5. That's our default portrayal, and then we can make amendments depending on whether certain characteristics of our agents are true. So we could have different colors for infected and non-infected agents, for example. So then we can say, well, if the agent is infected, then change the color bit of the dictionary to red and make the layer 0. In other words, put them on the bottom. Otherwise, change the color to gray, put them on layer 1, so they'll appear above our infected agents, and make them smaller. So essentially, we should end up with large red circles on the bottom for agents who are infected, and small gray circles on the top for agents who aren't infected. And then we just return the portrayal from that method. And that basically just says that's how we want to draw agents. And then we set up the visualization elements. So we set up a grid, because we want the grid to draw these agents. So remember, we imported canvas grid. We pass in the portrayal to that, so that will define how we want our agents drawn on that grid. And then we set up the size of that. So we want it to be 10 by 10 cells and 500 by 500 pixels in size. But there's also another element I want here, as well as the grid. I also want to draw a graph, so I can monitor the total number of infected people over time. So I've called that total infected graph. And here, that's why I've imported the chart module. So into that, I'm going to pass in a dictionary, which gives some information like the label. That label has to match whatever it is you're tracking. So remember, back in the back in the model class, in the data collector, we set up as one of the reporters total infected. That name has to match whatever we're putting in the server, because that's the thing it's going to grab. So it'll say, okay, that's the thing that I am. That's the data collector. Sorry, the model reporter within the data collector that I am plotting. And then the color for that line I'm setting up as red. So we'll have a red line that tracks the total infected over time. And you can find all that in this data collector, which I've just called data collector, because that's what we called it back here. And then, so we've got a grid set up, which will visualize the agents. We've got a graph set up, which will monitor the number of infected over time. I'm going to set up some user interface sliders so that the user can play around with the numbers and change different parameters. So I'm going to set up a slider so they can change the number of agents. And remember the format here we use, we give the name of the slider, and then we say it's a user settable parameter. The first attribute we pass is that it's what type of parameter it is, a user settable parameter, and it's a slider. They're all sliders in this example. The label that we want to be, so that'll be the little bit of text that appears next to it to indicate to the user what they're changing. Then we have the default value for that slider, so we'll default to 20 agents. The minimum that the user can change it to, so in this case 2, the maximum they can change it to, in this case 100, and then the increment of change, so each time they go up or down a notch on the slider, how much will it change? And in this case, it'll be 1. And I've done that for all 5 of the things, so the probability of initial infection, level of transmissibility, level of movement, and the mean length of disease. And then once we've got all those bits together and set up, then we basically just plonk it all onto the server and tell it to run. And so we set it up as a modular server. We pass in our disease model that we've written back in the other file. We pass in as a list the visualization elements that we want. So in this case, we've got a grid that we set up above, which is where our agents will be visualized, and a total infected graph, which is the graph up here, which will monitor, plot our total number of infected over time. I've got the title for the what I want to appear on the title of the browser, the disease spread model, and then we just pass in a dictionary here that has all the elements that we need to specify. So we've got a number of agents slider with a width and height, our infection slider, transmissibility slider, etc., etc. And so we then pass it the list of these sliders that we've set up above that we want it to visualize. So we're just telling it that we're wanting it to visualize this model with these visualization components, with this title, and with these user parameters, user setup parameters. And that's all there is to it. And that basic structure of having your model with your agent and model classes and your data collectors, having a run file, and optionally having a server file which will define how you portray it, underpins all agent-based simulations that you do in Mesa. So that was a bit of a whistle-stop recap. Hopefully that's triggered some stuff back from last time. Let's hope so, because I'm going to launch you now straight into an exercise where you're going to get some practice, a bit more practice at building a model in Mesa. So what I want you to do is to expand this model to add in the potential impact of immunization against the disease. Let's imagine we are building a model of a disease and a vaccination program is being proposed, and we want to model what we think the impact of that will be. So what I want you to model here is to model this impact of immunization, and specifically those who are immunized against this disease will be immune from catching the disease for an average of 20 days. Now that will be exponentially distributed, so you need to randomly sample the length of time they will be immunized, but it will be an average of 20 days. Now, immunization is only effective when administered when the individual is not infected. So if the agent is infected, then effectively they can't be immunized. Every day, so every time unit of your model, there's a probability that each non-infected person will become immunized. So I want you to modify the model to capture this. I want you to include sliders on the server that allow the user to alter the percentage probability that each non-infected individual is immunized each day. I want that to default to 5%. So by default, every non-infected agent in the model, every day, there's a 5% chance that they will become immunized. And I want the average immunization duration to default to 20 days, but I want that to be a slider as well, so the user can change that. For simplicity, we're going to assume that nobody's immunized at the start of the model. Okay, so you don't need to worry about setting up and calculating whether anybody's immunized at the start. I also want you to capture and graph the number of immunized individuals over time. So just as you did for the number of infected, I also want you to capture the number of immunized individuals. And I'd recommend you do that on the same graph as where you're plotting the number of infected. So you can effectively have two lines on that graph, one that shows the number of people infected and one that shows the number of people who are immunized. And I also want you to represent immunized people on your grid as a different color. So we've got, at the moment, we've got red people who are infected and gray people who are not infected. We want a different color for those who are immunized, who by definition, given the above, must be not infected. I want you to work in small groups to do this. I'm going to put you into breakout rooms, and I'm going to give you about an hour-ish to do that. I'm also going to give you a few extra hints that are on this slide, but I'll let you sort of read through those in the slide notes. But have a good look at what you're being asked to do. Have a look at the model that you've built so far, and think about how you're going to build in this concept of immunization. And then once you've built it, once you've built in this extra functionality and you've got the visualization for it, I then want you to play around with the model and see what happens. So what level of immunization do we need to get to in order to try and wipe this thing out quickly? Okay. Any questions about any of that? No? Good. Okay. I will split you into groups. So I'll give you about an hour, but make sure at some point in the hour you take 5 minutes to stretch your legs as well. So if we tentatively say we'll come back about 5 to 10 past 11, but I'll send an update a little nearer the time. So if I stop sharing, pause the recording. Okay, so I'll share my screen. I'm in my one online. Yeah. Okay. So yeah, basically we wanted to add in this concept of immunization. So we had to sort of put it in at various points in the model. So one of the first places we need to put it in is when we define what a person agent is. Now I've put in two extra attributes that are passed into the agent. One is the mean immunization duration, in the same way that we had a mean length of disease. One is the probability that they'll be immunized on any given time step. And so we need to do something with these extra things. So here I've just got the mean immunization duration. I just store that as whatever is being passed in against the person agent. And this is all the same as before, but then we also then need to do something with the immunization flag to indicate that whether the person is immunized or not. So at the start, we're going to assume that everybody is not immunized. Nobody's immunized at the start. So I'm going to create in the constructor just an attribute called immunized, which I'll store against the agent. And I'm just going to set that hard-coded to false. So everybody at the start will not be immunized. I'm then going to set up much as we did for the disease duration, set up an immunization duration that will store basically how long they've got remaining on their immunization if they're immunized. I'm going to start that to 0 because nobody's immunized at the start. And an attribute that stores the probability of being immunized in each time step. That's the one we've passed in, the probability of being immunized. And I'll store that against the agent. So basically, we've got 3 new things stored against the agent. The immunization duration, the mean, the probability of being immunized, and the Boolean, which indicates whether or not they are immunized, which we can update to true or false as time goes on. And also this extra bit that I've just added in, this duration, so we can monitor if they are immunized, how long have they got left. The movement function will remain exactly as it was before. Nothing changes in terms of the way they move. The infection will be a little bit different though, because we need to make sure that we're not infecting people who are immunized. So as well as checking to make sure that they're not infected, we also need to use the and keyword to say, and also they can't be immunized, because if either one of those are true, either already infected or they're immunized, then they can't be infected. So we just add in the and statement there to do that. That's all we need to change in the infect method. Here's where we add in our extra method though, because we needed a method as well as a method to infect people. We need a method from the agent side to say become immunized, because on each day there's a probability that they will become immunized. And so this method defines the things that need to happen if somebody is becoming immunized. And there's basically only 2 things. So if it's decided that they do become immunized on this particular day, then there's 2 things that need to happen. We need to update our Boolean flag to indicate whether they're immunized to true. And we just need to sample the time that they'll remain immunized, which remember had an average of 20, but we're going to randomly sample for an exponential distribution, just as we did for the infection, if they're infected. So remember, this function will only be called if they are immunized, if they're going to become immunized. So tell the Boolean flag that they are now immunized, and work out how long they're going to be immunized for.
So would you always put the if statement not in there, but before then?
Yes, because so you could do it in there, but really what you want to do is to have a meta logic that says, if they're going to become immunized, run the function that makes them immunized, because it goes back to your functions should be atomic. They should do, I think Tom said the other day, one thing very well. And that's basically what a well-written function should do. So here it's, if they're going to become immunized, then you'd call this function which makes them immunized, essentially.
Okay.
Then in the step method, this will remain largely the same, but we've got to add in a couple of extra bits. So all this first bit is the same as before. But of course, as well as getting them to move and then see if they're going to infect other people, we need to do this immunization check, because if they're immunized, then we need to decrement the remaining duration of their immunization by a day. If they're not immunised, we need to decide whether they're going to be immunised on this particular time step. So if they are immunised, we've got an if statement here, then just as we did for the infection, we'll decrement the immunisation duration by 1, and then check to see if it's now 0 or less, and if it is, then we'll set the immunised Boolean to false. However, if they're not immunised, we have to do something. So before, if they weren't infected, then we didn't do anything. But here, if they're not immunised, then they may become immunised. So we need to add in this else statement here. And we're just going to do a check against the probability of being immunised, which we've got stored against the agent, and sample from a uniform distribution. If it's below that threshold, then the agent will then become immunised. So all we need to do is then just call that become immunised function that we've run up here, and that'll do the magic for us.
Do you define when to use a normal distribution rather than another distribution? Because there you've just got a normal one.
So here, well, it's the uniform distribution that we use.
Yeah.
Uniform distribution means there's a equal chance of anything
Yes.
being selected. And that's what we want here, because we're basically saying, pick a number between 0 and 1, and use that number to compare against this threshold. And if we do that, we know that, so if the probability of being immunised is 5%, then 5% of the values between 0 and 1 will be the same as that probability. So if you pick a value between 0 and 0.05,
yes,
5% chance of that happening on a uniform distribution.
Right, okay.
So that's why we use it for that sort of threshold comparison. But if you're using it to work out a duration or something like that, you'd use something like the exponential distribution or a log normal or something like that. So that's why we use the uniform here, but when we work out the duration, we're using an exponential distribution.
Okay.
So in the disease model class, much of this again will remain as it was before, but we've got to remember that because we're going to create our agents here, we need to add in the extra things that it'll need when it's creating an agent. So we added in that an agent also now needs a mean immunization duration and the probability of being immunized. So we're going to need to pass that into the model so that when it goes into the for loop, it can also pass those things on to create a new agent. Because remember, you've redefined an agent as also needing these 2 extra things now. So we need to pass that through. All of this will remain the same. There is a difference down here, though. The data collector, we also want to track the total number of immunized over time, as well as the total number of infected. So I'll come on to it in a second, but we've written an extra function down here called calculate number immunized. So we need to add that into the model reporter so that it tracks that over time. Everything else, though, in the model class will remain the same. Obviously, our calculate total number of infected function will remain the same because that isn't affected. But we have got this brand new function called calculate number immunized, which will allow us to track that number over time. This is exactly the same as the other functions, practically a copy and paste job, except this time, instead of looking at the Boolean for whether they're infected, we're looking at the Boolean to see whether they're immunized. So that will grab a list of trues and falses indicating whether each agent's immunized or not at this particular time point. And then it'll count up the number of trues, and that's what it'll return. And because that's being called by the model reporter in the data collector, then it'll monitor that number over time. That allows us to plot it, etc. So that's all the same apart from that extra function. Your disease your disease run py file will be exactly the same. That doesn't change. And then you've got a couple of extra bits to put into your server file. And it's basically just because we want to do 2 extra things. The first thing we want to do is to color our immunized agents a little differently. We want to, so in this case, I'm going to make them blue. So I'm just adding in an extra bit of logic to the if statement here to say, already we said if they're infected, then color them red and put them on this layer. I'm just going to add in an elif statement to say, but also if they're immunized, remember they can't be infected and immunized at the same time, then color them blue, put them on layer 1, and I'll make them 0.2. So they'll be the same size and on the same layer as those who are not infected, but they'll be colored blue to indicate they're immunized. So we just add that extra little bit in there. and then in the grid, for the grid visualization, we also then need to, for the graph visualization, we then need to basically add in an extra line to our graph. So I've changed the name of my graph to total infected and immunized graph. Obviously you can call it whatever you like, but and what I've done here, as well as putting in this, I want a red line tracking the total number of infected, I also want a black line tracking the total number of immunized. So that will do it on the same graph. You could set up a separate graph and have one graph that tracks the number of infected and one graph that tracks the number of immunized. But it's quite neat for this to look at them on the same graph, and so you can do it within the same graph there. And then the last thing we need to do is just add in a couple of extra sliders so that the user can change these new parameters. So I've got a probability of immunization slider here, which will link into the probability that they're immunized. That defaults to 5%. And the mean immunization duration slider, which is in days, which will default to 20 days on average. And the user can then change that between 1 and 100. And then as well as setting up the sliders, we need to then link those back into the parameter values that are being changed. So probability of being immunized, that value is going to be affected by the probability of immunization slider here, and the mean immunization duration is going to be the mean immunization duration slider here. So that's where you link essentially the whatever values on the slider to whatever value you're using in your model. So, drum roll, if I run this, hopefully it will work. So if I go back to my run file, let's see what happens. Okay, can you see the browser?
Yes, Dan.
Yep, brilliant. Okay, so this all starts off exactly as it was before, looks identical apart from these extra couple of sliders. But you can see on the graph here, we've got an extra thing on the legend says total number of immunized, and that'll be a black line. So I'll start it off at 5%, we'll see what happens. So we can see little blue dots appearing as people get immunized. And if we look at the graph over time, we can see more and more people getting immunized. As the number of people getting immunized increases, the number of people that are being infected decreases, as you would expect. So it looks like we're building up a bit of herd immunity to this. And there we go. So we've now built up herd immunity and we've eradicated the disease. And that only took us basically vaccinating 5% of the population per day. I say only, that's quite a lot.
That's amazing, because you've only got mean length of immunisation is just a few days, 20 days? And
yes.
Still you've got herd immunity.
Yes, although this is a very small population of 20 people. So you've only got to remember the infection can only come if somebody's infected.
It just looks like there's more people in that box there.
Yeah,
dots.
Yeah. So if we were to change that, so let's say that actually let's reduce that a little bit. We'll leave the probability of immunization the same. I'll make it more infectious, and I'll make people move around a little bit more, and I'll make the disease last a bit longer. And let's see if it's as effective as it was before. Let's put in more agents as well. So here we go, we've got somebody immunized, somebody's being immunized there. So people are getting immunized, and that's working, but there's a lot of infected people floating around. So obviously the number of people that can be immunized is reducing, and at the moment doesn't look as though we're managing to get on top of it. People are getting immunized, but the immunization I've changed to only last 10 days. So obviously they can get reinfected unless we can get on top of it and remove the disease from our population. Then they're going to keep getting reinfected, and you can see actually here that's exactly what's happening. So we had a bit where we looked like we were getting on top of it. We had more people immunized than infected, but now we're starting to get very high infection numbers again. So we're getting some immunity, but we've still got the thing floating around. That's unsurprising. I've got a very high level of movement and a very high level of transmissibility, and the disease lasts a lot longer.
This is fascinating, because if you looked at the bottom, you'd think that there was something abnormal going along there. You know, if you were looking at your data normally, when really there is nothing abnormal at all. It's just a random sort of process.
Yeah, that's right. It's essentially it's a balancing act. You're trying to um, you're obviously immunizing people, which
Yeah.
removes the probability that they could get infected.
Mm.
But if you've still got enough, if you're not immunizing enough, or the virus is still spreading and it's infectious and people are moving a lot, then obviously you're not managing to contain it, and so it's running out of control basically.
Mm. It just makes you realize how we assume things that we shouldn't assume.
Yes, yeah, very much so. So I'll post that solution to Slack as well later, and to GitHub, and compare against your code, because as I say, I think in both groups you were very, very close. You were not far off at all, so you were nearly there. So have a look at that, see where the bits you needed to add in, and I'd make those changes to your code if you can when you get 5 minutes, because it's worth playing around with this, because it's a really nice sort of visual interface that allows you to see things really clearly. Okay, so let me press on. So also hello.
Would you mind that the line that gets the parameters from the slider?
Yeah.
Could you just talk that through for me?
Yep. So so these bits down here, you mean?
Yeah.
Yeah. So basically what you're doing, so up here you set up the sliders. You're saying I've got a slide. So if we look at the mean immunization duration as the example, we're saying we've got a slider that's called mean immunization duration slider, and that's basically a user settable parameter that's a slider. That's the bit of text I want next to the slider, and these are the default min, max, and increment values for that slider. But then, of course, we need to link it back to the what value in the model is it going to change. And here's where you do that when you set up the server, because you pass in the model. So that disease model we imported right back at the start. We said from disease model, which is the name of our file, import disease model, which is the name of the class. Mm-hmm. And then so it knows that's the class that it needs to look in for the model. Mm-hmm. And then down here is where we, in this little dictionary, we basically have a set of key value pairs that indicate, so the key value is the name of the parameter that the model's expecting. So mean im duration is what I've called it in mine. So if I go back to the model, you can see it's expecting a value called mean im duration. Mm-hmm. So there, you then link that to the value of the name of the slider. So that's where you link it. So it basically says whatever value is in that slider, give that to mean im duration, and that's what it'll pass into the model.
Right. So those have to be exactly the same.
Yes. Yes. You'll get an error if you called this something different. You'll get an error saying I don't know what parameter that is.
And you called that at the start of the other disease model. You that's where you said look in modular server for all of these variables. Is that right?
No, that'll be, so basically the way it works is you run the run file. The run file then launches the server, because that's all you've told the run file to do. So then that runs this file, and then this file imports the model, and it says run this model on a server, and then basically the server then runs the disease model class in here, which then in turn runs, creates the agent, and then runs all the rest of it. So that's the order it works. It basically, you run the run file, which launches the server, which sets up all of your browser stuff, but then also starts the disease model running, which then sets in motion everything else that you've written in your file, basically.
Right. Okay. So you set the disease model running from that line 58 and with those parameters.
Yeah, because that's the server being set up, basically. And then the server deals with it. So that's unique to Mesa. So that's the way Mesa does it. That you have a run file. Remember, you don't. So I'm about to show you where you don't have a server. And
sorry, the server is just your name for it. Yes, it's the modular server is part of this, but it's just what they call it, isn't it?
Yes, the modular server is a Mesa class, basically.
A class within this, yes. Yeah. So it doesn't really need to be called server, because that can be quite confusing when we think of normal servers.
Right, I see. Yeah. Well, I mean, that's essentially what it is. That it's launching a server on your computer.
Right. Okay. Okay.
And that's then serving that web page.
Okay.
The browser, and then that basically what that browser web page is doing is then running your model in the background and then visualizing it on your browser.
Okay. Can I ask about the grid? At the
Yep.
moment, you're just defining a piece of an area, but could we change that to the UK?
Yes. So in what way? Sorry, do you mean?
So where you've got grid equals canvas grid, agent portrayal here, instead of doing it, grid equals and then a geographic area of the UK?
So they still need to operate on some sort of grid.
Yes.
So what you would do is to have some sort of, you'd need to convert your geographic real world representation into a grid representation, essentially.
Yes.
If you were doing that, you'd probably have much more advanced movement rules, for example, that you're not just randomly moving between cells, that your cells would represent particular pockets of geographic area, and then you'd have rules for how people are moving between those areas.
And it could cope being within a sort of weird shape, could it? Doesn't have to be this sort of very angular shapes that you defined here.
Well, it would still need to be a grid structure.
Yes.
You could set up rules that, so if you're trying to emulate that people couldn't move north, for example, at a particular point, then you could emulate that.
Yes.
Probably though, that's not the way you'd want to do it. You'd probably essentially use your grid would be more abstract than that. So you think about each cell not necessarily as a geographic representation of, you know, this cell is north of this one.
Yes.
Your cells as being, this represents the city of Plymouth, for example. This represents the city of Exeter. There's a movement distance between those things.
Right.
And then you would have a transition between. So your grid is kind of representing a more abstract notion of people's movements.
Okay.
Rather than you could do it as a, you know, trying to get a more exact geographic representation, but that would be a lot more complicated to do. And of course, you then need to have a lot more information about exactly how people are moving.
Yes.
Whereas the likely information you'll have is more abstract than that. It's in terms of people's general movement patterns between particular areas, for example, rather than going 2 miles up the road or something like that.
Yes. Yes.
Okay. Does that make sense? Any other questions on any of that? Okay. I say have a look at the solution. Make sure you sort of understand all that. But basically, this structure in Mesa that's basically your basic agent-based structure. You've got agents, and you've got they live in a model, and the model schedule runs the agents essentially, and then optionally you've got this server that will then run the model and serve it out to a web page. But I'm about to show you what to do if you want to run this model lots and lots of times, and you didn't want the server bit, because actually in reality, if you're building up your model and once you've got approval from your collaborators that this is a good representation, then you probably want to run it to actually generate some results from it. So we can do this really easily using Mesa. It's got a built-in library that's called BatchRunner, and basically what we can do is we can use BatchRunner to say, okay, I want to try lots of different combinations of vaccination probability. So I want to try everything from 5% to 50%, and I also want to try each of those things with a level of movement between 0.1 and 0.2, for example, so that suddenly you get into lots and lots of different combinations. Now you could just run the model for each combination, make a note of the results, save the results, then move on to that. But obviously if you've got lots of combinations, that's going to quickly get tiring. So a better way to do this is to use BatchRunner, and then you can basically tell BatchRunner, these are all the combinations of things I want to test. Go away and test them for me. And it'll run them really quickly for you. So basically what we do is we say, I want these parameter values to remain the same. I want these ones to change. I want to run the model this many times for each combination, and BatchRunner will do everything else for you. So let's look at how we do that. So the first thing we change is the disease run file. So up until now, the run file has basically just been these 3 lines of code that tell it to basically launch a server this port on your computer. Now, what we want to do here, we don't want to run a server. We want it to just run the model lots of times really quickly. So we're going to change this, but it's good practice. You probably do still want to have that server available, so that if you want to show someone your model, you can launch the server and they can watch what's happening and they can see how the model works. So a good practice is just to comment those 3 lines of code out. So you can write all the rest of it, and then if you want to do the server stuff, you can just uncomment this code, comment the other code that you write, and then you can easily switch between them, depending on what you're wanting to do at a particular time. So just for now, just commented out those 3 lines of code. And what we're going to replace it with is basically this. So rather than, we're not going to launch a server at all now, we're just going to get it to run using a batch runner. So the first thing I'm going to do is import everything from disease model, which is my disease model.py file. The wildcard, the asterisk there, just means import everything. So it'll grab the person agent class, the model class, the functions, the lot. We want everything. So with the server, we only imported the disease model class, and then it launched because Mace has got that built in, it then runs the disease model class, and then that starts off a chain reaction. But here we need everything imported. I'm also going to import something from NumPy called arange. I'll explain, you'll see why that's a useful a module in a moment, but basically arange allows us to create evenly spaced numbers within a given interval, which is can be quite useful for stuff like this. I'm also going to import matplotlib, pyplot, so we can plot our results. And I'm going to import BatchRunner, which is going to do the magic for us. So to do that, we just say from mesa.batchrunner import BatchRunner. Then what we'll do, this is all still within the disease run file, we're going to set up a dictionary, and the first dictionary is going to say, here are all the values that the parameter values that will remain the same. I don't want these to change. I'll have these fixed. So here I'm going to fix the width and height of the grids. Will always be 10 by 10 cells. I don't want to change the initial infection. That'll always be 0.8. Transmissibility will always be 0.5. Mean length of disease will always be 10, etc., etc. So all those things, it'll keep the same for every run. It'll always make sure they're set at those values. And then I can set up another dictionary that says, these are the values I want you to change. These are the ones that I want you to try running the model with this set of parameter values, and then with this set of parameter values. So let's say that I wanted to change the 2 things in my model: the number of agents, which remember is n, and the level of movement, the probability that an agent moves on any given time step. Let's say I just want to try all of those different combinations. So all the combinations of agents between 2 and 100, and because there's no point having a 1-agent disease spread model, and different levels of movement between 0 and 1. So going from nobody ever moving to people moving it all the time. And all you do is you set up the dictionary, and we give it the name of the parameter that we want to change, and then we specify the range that we want it to change between. So for a number of agents, n, I give it the range 2 to 100 in increments of 1. So it'll test every number of agents between 2 and 100 in increments of 1. So 2, 3, 4, 5, 6, etc. And then also for each of those, I also want to check all of the levels of movement. So it'll first go through all of the scenarios where you've got 2 agents, and then it'll check all of the different levels of movement that I want to test for 2 agents. And then it'll do the same for 3 agents, and then for 4 agents, etc. And here's where we use arange. So here I want to specify a level of movement. I want that to change. I want to test everything between 0 and 1. And because we've got a floating point number here, I can't just use the standard range method. That won't work. So I need to use arange to give me evenly spaced floating point numbers. So I'm saying here between 0 and 1 in increments of 0.1. So essentially it'll test a 0% level of movement, a 10%, a 20%, 30%, etc., all the way up to 100% for each of these combinations. So you can already see, just by changing those 2 things, there's quite a number of combinations you'd have to test, because essentially you're testing all of these different levels of movement for each of these numbers of agents. So having something that will automatically do this for us and then give us the results sort of nicely output is really useful. So we're also going to need in our run file to specify the number of iterations to run for each combination of parameter values, and also the number of time steps in each run. So here I want each combination to run 5 times. So if I've got 3 agents and a level of movement of 0.6, I want you to run that 5 times so it can take average results over those 5 runs. And each run should run for 365 time steps. So my time steps represent a day, essentially a year. So simulate a year's worth of time, do that 5 times, take the averages over those results, and do that for every combination that I've specified. And then we just need to basically create the batch runner with all of this information in. So we've imported BatchRunner. So I create a new BatchRunner, a new instance of the BatchRunner class. I've just called mine BatchRun. And into that, I pass the disease model, so the model class that we've imported. I tell it what the fixed parameters are. So fixed parameters equals, and then remember I created a dictionary called fixed params here. So basically use that. Same with variable parameters. I created a dictionary called variable params, use that. Iterations is the number of iterations that I specified here. Number of max steps is the number of steps that I specified here. And then I also need to give it the model reporters. Remember, these are the outcome measures that I'm interested in. What are the results I'm interested in? So let's imagine it's the same as before. I want to look at the total number of infected over time and the total number of immunized. So I just pass in my model reporters in the same way I did in the model class. So I give all that information to the batch runner. I say, this is the model I want you to run. I want you to keep these things the same. I want you to change these variables. I want you to run each combination this many times. I want you to run each run for this amount of time units. And I want these results to be the ones that are reported. That sets up the batch runner. Then we just need to tell it to run all of those combinations. So we just say, we use the run all method of the batch runner, which I call batch run. Then I'm going to store, because I'm going to get a lot of results out of this. So I'm going to store the results into a pandas data frame. And I can do this by calling a method that is got built into the batch runner called getModelVars data frame. And if you call that, it'll automatically take all of the results that it's collected and it'll store it automatically for you in a pandas data frame, which is really nice. It allows us to do that without us having to do anything. And then let's say I wanted to plot a scatter plot of level of movement versus total infected. I could then run a scatter plot just by grabbing the level of movement. Remember, this is now a pandas data frame, so I can just grab the level of movement versus total infected, or whatever else I may want to do for this particular model. So all of that basically goes in the run file that you set up your imports here, your fixed parameters, your variable parameters, number of iterations and number of steps. Then you set up a batch runner with all that information. You tell it to run all the combinations, and then you store that in a pandas data frame just from that using this getModelVars data frame method, and then do whatever you like to it. So here I've just done a scatter plot, but you could do whatever you like. Now, you may be starting to think here, oh, this is brilliant. I could test all of these combinations of all of these 20 parameter values I've got. Be extremely careful. Agent-based simulations are already computationally expensive to run because they're quite complicated in terms of the math that's happening underneath. They can take a while to run. So if you're testing lots of different combinations, you can very easily end up with thousands, hundreds of thousands, even millions of different combinations just through testing 10 different parameter values, for example. Because if within each one you're testing 100 different ranges here and 200 different values here, that's all going to multiply up. And so you're going to end up with a huge number of different combinations that will take a very long time to run. The first time I did this for this training program, I forgot that and actually had a thing set up that tested so many different, I think it was only about 5, 5 parameter values, tested lots of combinations of those. At the time, Mike had the fastest computer. I set it to run on Mike's computer. I collapsed Mike's computer because it took a best part of 45 minutes just to draw the pandas data frame to store the different results. It didn't even get on to running the combinations itself, and it ran out of memory and collapsed. So be very, very careful, because it's easy, because this batch runner is so easy to use and it's so easy to specify different combinations really easily. It's easy to get carried away and forget how many different combinations you are testing. So be mindful, particularly if you've got a slower computer. It will make it even worse. But even if you've got a super fast computer, you're going to run into problems very quickly if you try and test too much at once. So just to close off with today's session, a little final task, and give you a bit, running a little bit over, so I'll give you a little bit less time to do this, but I think it'll still be good for you to do this. I'm going to split you back into your groups, and now you've seen an example of agent-based simulation. I want you to think about some other ideas about how this kind of modelling method could be used to tackle problems in your own organisations. So I'm going to give you about 20 minutes to about 20 past 12, just to have a chat in your groups about some potential applications for agent-based simulation. Now, you're probably not going to have time to draw up a design about that, but do think about what your agents might be, and what the environment might be, and what the interactions would be, and the questions that they'll be trying to answer. So come up with, have a quick chat for sort of 5-10 minutes initially to think of some potential ideas, and then run with one of those ideas and spend another 10 minutes just thinking about how you might design an agent-based model around that. What would your agents look like? What would their behaviours be, etc. Okay, I'm going to split you back into your groups, have a chat, and I'll bring you back in 20 minutes, and I'll ask each of the groups just to present their thoughts on this. Pause. So I'm interested now to hear some of your thoughts. Good discussions going as I dropped in. So if I can ask group 1 to feedback first. So that was Imka, Josh, Juliet, Matt, and Zoe.
Well, we decided it's incredibly hard.
Okay.
Very, very hard. Knowing the other models that we have, they seem more applicable. But we did decide that it's to do with independent. The agents are not independent, but they interact among themselves to changing things and to do new things. So they've got to be something that's independent, but they interact. And it's finding that thing. So we were struggling about whether we had a set of services. So we've got the GP, the 111, the 999, and the acute unit services, and urgent care service. And first of all, we thought, well, is each of those an agent, and how they interact together?
Yeah.
But then, should each of those be the patients? We got really confused, to be honest. It's extremely hard.
So you can, something's worth flagging up actually. So that, obviously what we've looked at so far in terms of agents is that, your agents have essentially been people. And when we talked about the ecological stuff, we talked about, the agents being animals. But they don't have to be. I mean, so your agents can be organizations. You could have things like, a hospital, various hospitals as being your agents, and the way in which they act and interact with each other is what you're modeling. So you can have sort of organizations as being your agents, absolutely.
Yeah, but they'd be different organizations, and your agents are all the same, and that's the difficulty. We don't want all the hospital acute units. We want different types of emergency services.
So you could have that. You could have different types of agent in your model. So you could have, for example, you could have an agent that was like an acute hospital, and then you could have various properties that you could. Each of those can be as unique as you want. So you could set up, various attributes according to what you want to set up for that particular agent. Or
Right.
you might have then different classes of agent for different types of organisations are separating them by, you know, acute and GP surgeries and whatever else it may be, and then have differentiation within that. So you could absolutely do that. Yeah, it depends obviously what you want to do with it, how you would approach that. But there's I mean, agent-based simulation is one of the most open-ended of the modelling methods that we use, and that can be its power, but it's also sometimes its drawback, because it means you can effectively do anything, but then you have to try and work out how you would do that.
So if we had the agents and we define them as for the Southwest, the number of GP surgeries, the number of acute ED departments, and the number of urgent treatment centres, so they're all defined and definite, then how do you then pass the people through that sort of service? So how do they fit in?
So if that's what you're trying to do, maybe then agent-based isn't the way forward, because it depends what the question is. So I think
yes,
if we're looking at those as being the organisations as being the agents, then you're probably not trying to do a sort of queuing type question. So you're less interested in that. You're more interested in what is the behaviour of this agent, i.e. the organisation as a whole. So then you'd have to find ways, can we describe the behaviours that we're interested in and the way in which they interact with other organisations? Can we describe that in a way that we can put that into a simulation model?
That is sort of what is interesting is the fact that they don't support each other, and they do the easiest thing and pass over onto one of the other emergency services.
Yeah.
So that is the behaviour of what's happening, and if you could somehow show that, then they would understand how the effect of this behaviour of just passing over rather than dealing a little bit more slowly and resolving things at earlier stages.
Yeah, absolutely. I mean, you could even, so we used to do a little workshop years ago now that was all about game theory and showing how different organisations can game against each other essentially by doing things because of perverse incentives in the system, that they can do things that will improve their reward, but in doing that, it sort of shunts the problem over somewhere else.
And absolutely, and we have that within our service. Those people that are working who are actually our top performers are actually more passing over onto other services than other people that are closing cases.
Yeah, no, absolutely. No, I think there's definitely something in that, I think, that could be looked at. Just looking at the time, so I'm just going to quickly go over to breakout room 2 just to feedback. So what were the thoughts you had in that room?
I think I mirror the earlier statement that it is quite difficult because the agents we're modelling are complex, and we don't actually know all their drivers. So from a policing perspective, one that we've looked at is the ability for agents to infect each other with criminality. Mm-hmm. So not so much the network analysis, but the alternative of how networks get built, and then applying a second group of agents of police or other law enforcement or social services over the top, which may then have the opportunity to essentially uninfect them with various levels of criminality instead.
Yeah, I think that's a really nice use of agent-based simulation, because I think that you're sort of taking that concept of because the reason the disease spread model is so widely used and is a good way to start with agent-based simulation, because it captures that core principle that you've got individual level behaviour that is driving a population level emergent behaviour. So by knowing how people are tending to move around, and the chances they infect someone else, etc., at an individual level, you can then say, well, what happens when you chuck that population in altogether? What happens, and what are the emergent dynamics that emerge at the population level? And so, yes, absolutely, you can think about that kind of disease model of being transferred over. Well, what if it wasn't a virus that we're talking about? What if it's unwanted behaviour, and that people being influenced by that unwanted behaviour negatively, in other words, being infected? Or what if you're put in interventions that people that could disperse that and combat that, almost like your immunisation, essentially. So yeah, absolutely, you could think of that core disease model as being not representing a disease in the virus sense, but in terms of behaviour in itself. Brilliant, thank you. That's really good ideas, and you're right. It is more difficult to think of ABS stuff. I mentioned to Greg Room 2 when I was in there that so we did a model a few years back that was looking at the problem of polypharmacy, so looking at people taking lots of different medications who've got lots of things wrong with them, and the issue being that most people then don't take all their medications as prescribed because, you know, it makes them feel rotten. And so can we use an agent-based simulation to model the behaviours that drive them to take their medication or not to take their medication as prescribed? Other, you know, how are they influenced by other people, etc. And what if we were to have different interventions? And what if, you know, we prescribed, rather than prescribing the most clinically effective combination of drugs, but then hardly anybody's taking that as prescribed, would it be better to prescribe this set of drugs which aren't as clinically effective, but have fewer contraindications with each other, fewer adverse reactions, and have more people taking them? And so you could use an agent-based simulation. We did a sort of prototype to explore how you might do that as well. So lots of ideas there. Obviously, nobody's doing an ABS, as far as I know, for your projects, but do think about how some of this stuff can be used. Great. Okay, we'll end there because it's lunchtime and I've talked for enough, and you've got another 3 hours of me this afternoon if you're coming along. So this afternoon session will kick off at 1:30. We're going to be doing natural language processing. We're going to be doing named entity recognition, which quite a few of you will be doing for your projects. So it's probably, I think we've got 4 projects that involve natural language processing in some capacity. So hopefully you'll find this afternoon useful. You'll see that actually using Spacey out of the box is incredibly easy, and then it's not difficult to train it, it's just fiddly, but we'll show you how to do that as well. Brilliant. We'll see you at 1:30. Thanks, guys.
Thanks, Dan.
Thank you.